19b, where the function is defined this way, and we have to compute this guy. So first, it's f of gamma z we need to worry about, and it's cz plus d to minus kth. So we need to work on this. The absolute value, that should have been more vertical. Oh no, now let's see. Yeah, let's work on this. It's a little weird. Let's split it to the real and imaginary part. So we write z as x plus I y, where x and y are real. Now, I think I've misunderstood this totally. This is a real function which we operate on, and then per definition, so I think this was all wrong. And was that what I had to show? Oh, sorry, that was a trivial question and I thought it was complicated. Show that it is bounded on F. But then we just choose epsilon equal to 1/2. And then it's bounded this way. And exponentially. And this part is only bound polynomially. So of course it's bound absolutely. Because in F, the imaginary part of y is larger than or equal to square root 2/2. That was B and C. So it's bounded on I'm still confused about B here. So that is, we have to show that f of z gamma no, it's g of h. Oh, it's fj, yeah. Of course, it's only a problem as z tends to naught, or tends to the cusp. I'll just write it on paper because I get confused with the new notation here, and these guys, which are the ones we want to show are bounded, or rather, yeah. So I'll just do it by hand and then show the result. Hello, had a break, had my lunch. My fingers are still cold, but let's see what I was doing. This is, of course, wrong, because this is real. These are real, and this is in general has an imaginary part. So there's a mistake there. Using the definition, this is what we get, and then we have a formula for this. It's formula 1, 2. And now what was it? Yeah. Cz plus d, the reciprocal value of the square times the imaginary part of z itself. So minus k halves times 2. And then these two we can put under the same absolute value sign, and then we get this. In the book they write it like this, oops, which I think is better. Unfortunately, all these vertical lines have the same size in the book. I think these two should be larger. This communicates as well, I think. Okay. See, I don't know if that I got that correct. Yeah, I think I did. Now, what are we going to show? We are going to show that g of z is bounded. For z in alpha j to minus first of f, no, we are going to show it's bounded on f. Well, wasn't that obvious? It drops off exponentially, so of course it's bounded. Yeah. And now comes E. It says F mark. All right. So that's not done at all. So I'll prove that it for any one of them is bounded. Then it will be bounded on F mark. And that means that g of that means z, we write that as alpha j to minus first of I, where I lies in f, and call that z. And then we can use this guy. I believe this was what we called fj. Exactly. And what did we prove about fj? That it's bounded on f. So that was D. E, it's bounded on H. So let's take any other any other guy. Gamma, is that a sensible one? Well, let's do that. Gamma equals a j to minus first alpha, where z lies in gamma to minus first of f. And then we do the same trick, or do we? I think we do. Let's try it. G so we need to show something about g of u, z, where z lies in No, we already wrote that. And then we write this as offset of W, where W lies in F, in the fundamental domain. And apply the formula above again. Here we have it. And it's this guy, the inverse of this guy, that's alpha. Oopsie, oopsie, oopsie. So we are actually having the side classes here being left side classes. So gamma lies in one of the alpha j gamma, meaning alpha j to the minus first gamma lies in gamma, which we then call gamma mark. Am I confusing stuff here? This is where we get it wrong. This is where we get it wrong. So gamma to the first is omega. What am I doing here? It's Z lies in here, and gamma can be written, here we go. No. Yeah, that was a little complicated. So gamma can be written alpha j times gamma mark, and this guy lies in gamma. So gamma to the minus first is gamma mark to minus first. We just write that. Alpha j up to minus first. Okay, and numeric. And G is invariant under, and now what was that? It should have been alpha in front. So there's a little confusion here. We are dealing with left side classes. So gamma can be written alpha j times 1 in there. Oh, this is not all of them. What am I doing? Confusion rising again. Gamma is the union of gamma j to minus first f, gamma j, gamma mod, no. There we go. So that means that our gamma mark lies in gamma mark, which is a smaller group. And that's the smaller group where it's invariant. There we go. So G is invariant under gamma mark. And this, of course, is our Fj. Oh no, did I write G here? It's F, of course. So it becomes Fj of Z. Or shouldn't it be omega here? I think it should. And we already, where omega lies in F itself, and we have already shown that's bounded. That was E. When I read F, I thought, oh, I already did that. Oh, this must be a Y. Or rather, I didn't derive it, I just stated it based on Fourier analysis. Which I believe we must be assumed to know. But then it's plus y, then there's a minus here, and I squared is minus. That gives it here. Oh, then maybe that's quite all right. I did that right. Seems I did that right. So we can go to the next part. I'll just copy that to a new page. And then see what we can do. Now the max, so we choose F is bounded, so we have is less than or equal to some m. Well, that can be done manually. Oops, that's h, n divided by h minus unity. We'll just skip that. Right, and what did we have to show? Oh yeah, we are integrating over x. So that means we retain an I up here. And then there's no x here, so it just gives h. That as well. Times h. Two pi n y divided by h times a constant. There should actually have been y to minus k halves. That's because what is bounded is not f of z. What is bounded is g of z. And g of z is imaginary part of z to k halves times, yeah, we can just do it with f of z. So that's what is bounded. And this, of course, equals y to k halves. And that means that the constant we have here is m times y to minus k halves. So I'll just that's it. I think that's exactly what we should prove. Yes. Okay, that was G. And H. So we can just, yeah, let y go tend to naught so that this gives unity. Or, yeah. It holds for all positive. Oh, now what is that? Then this will tend to infinity as this tend to, oh, I see, we have to choose y sensibly. So that's n to k halves. Which we put into a new constant. So we have finally derived that for a cusp form, the values of an are bounded, and I'll be very surprised if the proof can't be carried over to any modular form, just disregarding the first term in all the relations here, which is a constant anyway. We have the same bound, the same everything, so it's just a Fourier transform of AJ instead, so it will give the same. Right. Well, that finishes section 3. I have learned an immense amount of mathematics.